So I wanted to take a closer look at diffraction. This is simply from your textbook, the Jacaranda physics textbook. And I wanted to look closely at this diagram because we have been looking at it in class. Now, what happens is you have a slit that has a certain width, W, or in some cases A. It depends on which textbook you're reading. And that width has to be around about the order of magnitude of the wavelength or less. So width is around about that or less. And if you have a slit that's around about that length, then you'll get a small amount of diffraction or a significant amount of diffraction. Diffraction is basically when you get two interfering waves which can interfere both constructively or destructively. So if you consider a wave emitted from point A and a wave emitted from point C, and this is due to Huygens' principle, which states that any position within that slit width could be considered as a source of point waves. And so you can look at two waves that are half a slit width away, for example, and know that they'd be half a wavelength out of phase. Back to our diagram. We want to look at the difference between AP and CP. So if we can look at the difference between these two lengths, CP minus AP, and when that is equal to half a wavelength, then we'll get destructive interference. And the destructive interference appears as a dark band. So you're not going to see a maxima, you're going to see a minima in your spectrum. And the first point of that destructive interference is going to occur at a particular angle. At a particular angle theta, you're going to get interference at point P, and that angle is going to be basically when sine theta is equivalent to the wavelength over the width. And that's basically due to the fact that you've got this wavelength difference here and the width difference there. The CB here is wavelength over 2, and AC here is half of your width. So what we're basically looking at is that very tiny triangle in the middle, which is looking at the relationship between the three angles there. So C, B, A, you have an angle theta, which actually ends up being over here, and this is wavelength over 2, and this is W over 2. So sine theta is wavelength over 2 divided by W over 2, or when you cancel out your 2's, wavelength over W. And that's how it works. And this occurs for your first minimum. When m equals 1, it will be the smallest angle for destructive interference. But we can also look at it and say, well, what happens when m equals 2? So this is basically saying instead of only half a wavelength, you've got 2 more. So you've got 2 wavelengths more. And for when m equals 3, again, sine theta equals 3 wavelengths more. So what does that mean? We now have a relationship for sine theta, which is in terms of m. And m is just an integer, 1, 2, or 3, or more. And it's just looking at the integer number of wavelengths. Or, for that example, the number of bands. So it could be the number of dark bands or the number of minima away from the central maxima. In your textbook, it goes through a few things, but it doesn't go through that derivation. That derivation is important because you need it for the double slit as well. What I want to do is highlight two things. One, when the wavelength increases, i.e. from changing from a light source that's from blue to red, the amount of diffraction will also increase. So what does that mean? When the wavelength increases, the diffraction increases. And when the wavelength decreases, the diffraction will decrease. This is a relationship here. But the amount of diffraction will also increase when the width of the slit decreases. So that's also saying when the width is going down, diffraction is also going up, which is important to remember. There's one more thing you can get from this relationship. So once you've got that relationship between the angle and the lambda, and I'll rewrite it again, so sine theta is equal to m lambda over W, which is your slit width. Yeah. You can also get a relationship for how far things are away. So if you can look at this relationship here, we have tan theta equaling y on L. And what we went through in class today was that relationship that at very small angles, less than about 15 degrees, sine theta is approximately equal to tan theta. So we now can set up an equation for these two. Y over L is equal to m lambda over W. Or if you want to set it up in terms of just y, then you're looking at m lambda L over W. And that is basically giving you the separation of dark bands for single slit diffraction. So that is for minimum. So we can use this relationship to look at various diffraction questions. This is one from your worksheet today. Laser light of wavelength 633 nanometers, so that's a red laser, is shone through a slit of 2 by 10 to the minus 6, so 2 micrometers, and the light strikes the screen a certain distance away. Calculate the angle for the first minimum. You sit there going, I don't know the angle, do I have enough information? But we do, because we've just set it up. Remember, we had sine theta was equaling to m lambda over W. In this case, in this particular worksheet, we've been using A, so I'll put A as the slit width. First off, we'll write down all the things. What is the slit width? A is equal to 2.0 times 10 to the minus 6 meters. Wavelength is equal to 633. I'm going to put 10 to the minus 9, which is nanometers. And we want to find out what theta is for m equals 1. That's the first minimum. So let's find out. We've got 633 times 10 to the minus 9 all over 2 by 10 to the minus 6. It's going to equal 0.3165, and therefore theta is going to equal sine of that, or sine to the inverse 1, which is 21.2 degrees. So the angle for the first minimum is around about 21 degrees.